Hello viewers, welcome to my talk about QStore. I'm very excited to present our queue-oriented approach for distributed deterministic transaction processing. My name is Tamer Qadah and this work is done in collaboration with Suyash Gupta and Muhammad Saduqi. Our research is motivated by the advances in cloud computing services. For example, major cloud providers such as Amazon, Google, and Microsoft are already providing virtual and distributed computing clusters that are equipped with terabytes of main memory and several hundreds of CPUs. Therefore, transaction processing systems that can take advantage of such modern computing environments can further provide business value to users and enterprises. In transaction processing systems, two-phase commit is the gold standard for committing distributed database transactions. It is a very good general solution and is widely used and implemented in many database systems. However, it adds a fundamental overhead per transaction. Therefore, the question is, can we avoid using two-phase commit for certain cases? Deterministic distributed transaction processing systems attempt to use a deterministic approach to address that question. The deterministic approach provides strict serializability and avoid transactional aborts related to concurrency control algorithms. More importantly, it removes the coordination required for committing a transaction from the critical path of each transaction. However, it suffers from some limitations. The major limitation is that it requires the knowledge of the full read-write set of a transaction prior to its execution. Now I will give an overview of Calvin, which is considered the state-of-the-art in distributed deterministic transaction processing. In Calvin, client transactions are sent to a sequencing layer. Each node in Calvin runs a single sequencing thread. The sequencing layer produces batches of sequence transactions. These batches are processed by the scheduling layer. Each node has a single threaded scheduler as well. A scheduler uses deterministic locking to schedule transactions on worker threads. Therefore, we pose the following question. Is it possible to avoid the two single-threaded pre-execution steps and improve parallelism during execution? We address this question in QStore. QStore combines sequencing and scheduling into a single-step phase called planning. This phase produces queues capturing the schedule of transaction executions. QStore provides a unified queue-oriented transaction processing paradigm for parallel and concurrent execution of transactions. QStore enforces a global execution priority invariant for execution threads to ensure strict serializable execution. Also, QStore provides support for speculative and conservative execution of queues as well as support for multiple isolation levels. In this video, we focus on the first two ideas. To illustrate the first idea, let us look at a high-level comparison between Calvin and QStore. On the left side is Calvin, and on the right side is QStore. QStore uses a single pre-execution planning phase. In this phase, queues of transaction fragments are produced instead of batches of sequence transactions. Furthermore, the queues inherit the priority attribute of their planning threads. These priorities are used to enforce ordering among queues produced by different planning threads. The next phase is the execution phase. In Calvin, a transaction is assigned to a thread, while in QStore, a queue is assigned to a thread. QStore can perform speculative execution of transaction fragments, which allows reading uncommitted data speculating that it would commit later. For processing transactions that do not contain abort logic, the speculative approach works very well. Now we illustrate the second key idea in QStore, which is our unified approach to processing remote and local queues. In this slide, we present a simplified architecture of a server node. We use dedicated communication threads to handle network messages. Communication threads are responsible of receiving transactions from clients and placing them in transaction queues. They are also responsible of exchanging remote execution queues among servers. We use worker threads to perform the two phases of planning and execution. During the planning phase, worker threads create local and remote execution queues. Remote execution queues are handed to the communication threads for delivery to remote nodes. Local execution queues are placed in the batch metadata in a lock-free mechanism. During the execution phase, worker threads execute transaction fragments from locally and remotely planned execution queues, while maintaining the global execution priority invariant. The batch metadata structure provides a unified abstraction for processing execution queues. The fact that an execution queue belongs to a remote planning thread is abstracted away from execution threads. We go over an animated example to illustrate transaction processing in QStore next. In this example, we have 3 server nodes on the right containing 6 records in the distributed database. Consider one execution queue for each record. At the top, we have high priority execution queues which are created by planning thread 1. And at the bottom, we have lower priority execution queues created by planning thread 2. Once all transactions are planned, they are ready to be delivered to the execution threads. This concludes the planning phase. Moving to the execution phase, we have 2 execution threads per node. Execution threads pick higher priority execution queues first to maintain the global execution priority invariant. After completing the execution of a queue, an ACK message is sent to the original planning thread. The write operation on record C requires the values of records A and E. The values of records A and E are received and are stored in the batch metadata. The write operation on record C can proceed now. Because the same planning thread had planned high priority queues, the planning thread can have the cached valid values of record A and E to be reused for the green transaction in this example. The process continues until all queues are executed with minimal coordination. Once all expected acknowledgements are received, the planning thread can respond to the clients who sent T1 and T2. We implemented QStore in ExpoDB, which also includes implementations of Calvin and other non-deterministic protocols used in our evaluation. We use a cluster of 32 virtual machine instances deployed on Amazon EC2. We use workloads based on YCSB and TPCC. Next, I'll present some notable results for QStore. In this experiment, we looked at only protocols that use batching, which are Calvin and QStore. The takeaway message from this experiment is that QStore can eliminate the bottleneck of single-threaded sequencing and scheduling layers and scale well while increasing the batch size. QStore achieves up to 22 times the throughput performance of Calvin and 95% lower latency on this workload. In this experiment, we study the effect of multi-partition transactions in the workload. We compare QStore against Calvin and non-deterministic protocols such as no-wait, MAT, MVCC, and timestamp. Non-deterministic protocols use two-phase commit for committing distributed transactions. With 0% multi-partition transactions in the workload, non-deterministic protocols do not perform two-phase commit, so their performance is high. Yet, QStore's performance is comparable to them. Despite the deterministic nature of Calvin, its throughput decreases as the rate of multi-partition transactions increase in the workload. This result shows that Calvin is sensitive to multi-partition transactions while QStore is not. QStore can achieve 10 times the performance of Calvin and nearly 30 times the performance of no-wait. In conclusion, it is possible to improve the performance and efficiency of deterministic transaction processing by using queue-oriented transaction processing principles. QStore can achieve up to 22 times the performance of Calvin and can provide up to 2 orders of magnitude better system throughput over non-deterministic protocols in our experiments. Future work includes studying and designing queue-oriented protocols for Byzantine fault tolerance database systems.